So we'll go ahead and start the exam review. Welcome to Math 2419 Exam Review 1. First, we'll quickly go over all the important topics that we probably need to know for the exam, and then we'll have a short break, and then we'll go into breakout rooms to practice some practice problems from the packet. So we'll just get started. So first, introduction. My name is Ritika, and I'm a PLT leader for Math 2419. And the other leaders, go ahead and introduce yourselves.
Hello, I'm Haley Saxey. I am a Math 2419 PLTL leader as well.
Cool, so this will be our agenda for today, and then we'll answer any questions that any students may have at the end. So the topics to be covered are 11.2 vectors, dot product, cross product, lines and planes, arc length surface area, and then parametrics as well as polar. And these will be all the topics that are covered on the exam on Friday. So we'll go a little bit into depth for each one and then see some example problems, and then we'll be able to actually work out some more problems. So before we start, there are a few trig identities that are really important to know, especially throughout this course. So the first one are the Pythagorean identities: sine squared x plus cosine squared x plus 1, 1 plus tangent squared x equals secant squared x, and then 1 plus cotangent squared x equals cosecant squared x. And some other important ones to know are the sum and difference formulas here, as well as power reducing and the double angle formulas. And the most important ones are definitely the Pythagorean identities as well as the double angle formulas. So starting with vectors in space, this is just an overview on what 11.2 mainly covers. So first, these are just some properties that the vectors have, such as equality of vectors. If each components are equal to each other, then the vectors will be equal. And then we can represent vectors in multiple different forms, one of them being component form. And next, to find the length of a vector, all you have to do is take the magnitude of the vector, which will be v1 squared plus v2 squared plus v3 squared, and square root of the whole thing, similar to a Pythagorean formula. And another important aspect is the unit vector, in which to solve for that, you just find the magnitude and divide the original vector by the magnitude. And then there are other properties of vectors, such as vector addition and scalar multiplication, that we will get more into as we do some more practice problems. So next we have the definition of parallel vectors, and this just states that two vectors are parallel when one of the vectors is multiplied by a scalar multiple of the other one. So that is the definition of a parallel vector. Now moving on to 11.3. The dot product is basically a scalar representation, and so the dot product of two vectors can be taken by multiplying each of the corresponding components. So if you have a vector u, u1, u2, and v1, v2, then to find the dot product of that, you would multiply u1 and u2 and add to, you would multiply u1 and v1 and add it to u2 times v2. And so you would result in a scalar answer. So moving on, here are some properties of the dot product. And the first property is the commutative property, which just states that it doesn't matter which way you take the dot product, you will get the same scalar answer. The second one shows the distributive property. So you can take the dot product of two vectors added to each other, or you can take the individual dot products and add those together. Next property is multiplying a scalar by the dot product. And so you would distribute the scalar to one of the vectors, not both. And that is because you don't want to multiply by the scalar 2 times. So that's what this property is showing you. Next, we have the zero property. If you try to take the dot product of a zero vector with another vector, you will end up with 0. And lastly, you have when you take the dot product of the same vector with itself, then you will get the magnitude of that vector squared. And some more rules about dot products include the vectors orthogonal, definition of the orthogonal vectors. So you know that two vectors are orthogonal to each other when the dot product comes out to be 0. And the angle between two vectors, here's another formula that involves the dot product. So cosine theta is equal to u dot v over the magnitude of u times the magnitude of v. So this can be implemented if you are asked to find the angle between two vectors. Next are some definitions of projections and vector components. So this is just stating, this theorem down here is telling you about two vectors and how to find the projection of u onto v. And so the projection of u onto v is denoted as u dot v over the magnitude of v squared times the v vector. So here is a sample problem about dot products. So if we can consider a vector u as being 1, -1, and 4, find a vector that is parallel to u and also perpendicular to u. So how would we find a vector that is parallel to u? Any ideas?
Vectors are parallel whenever they're scalar multiples of one another.
Exactly. So for this one, we would just try to find a vector that is a scalar multiple of u. And so it could be any example. And for perpendicular, we want to find, so for this example, for parallel, we find any scalar multiple, and the scalar multiple in this case was just 2. So our resulting parallel vector would be 2, -2, and 8. And so for the second one, for perpendicular to u, we know that for two vectors to be orthogonal to each other, which is the same as perpendicular, the dot product should be 0. So we can set up an equation to solve for the missing variables. And so we can plug in any points to solve for the third point. And for an example answer, we would get 1, 5, 1 as our vector v. So moving on to 11.4. So we have gone over a few topics so far, but those have been recorded, so the recording will be posted soon. But we'll just continue so that we can get to the practice problems, and then you guys can ask any questions you have throughout the session in the chat, or unmute yourself, and then we will continue with the topic overview, and then after that we will go into breakout rooms and do a couple practice problems. So moving on to cross product. In 11.4 we talk about how to take the cross product, and so the cross product will result u in another vector when you take the cross product of two vectors. And so the way to take the cross product is to put it in this 3 by 3 rows and rows and columns. So you can put I, J, K and take the cross product by multiplying the opposing columns. So here's an example. So in the first one, we would do only the multiplication of U2 and V3 and U3 and V2. So we're taking basically the determinant. And same for J and K. And so we'll do a practice problem next to show you how that works. So here are some important algebraic properties of the cross product. So first we have, if you take the cross product of U times U cross V, then your resulting cross product will be the same as if you take the negative cross product of V cross U. And next we have a distributive property. So if you do U cross V plus W and you add two vectors, then you can distribute that cross product to each vector and then add up the resulting. Next we have a scalar multiple, so you can distribute the scalar multiple to one of the vectors and then take the cross product, and it doesn't matter which one. And for the fourth property, if you take the cross product with a zero vector in any way, either U cross zero or zero cross U, you're going to end up with the zero vector. The fifth property shows that if you do U cross U, so if you do a vector cross itself, then it will result in a zero vector as well. And last, we have, if you take the dot product of two vectors cross, then you can actually do that in the opposite way as well. So you can do U dot V cross W, or you could do U cross V dot W, and you would get the same solution. So next we have some geometric properties of the cross product. And so U cross V is orthogonal to both U and V. So that just means that the resulting vector is going to be perpendicular to both of the other two vectors. And then the second property is the magnitude of U cross V is the same as magnitude of U times magnitude of V times sine theta. And the third property is stating that U cross V is equal to the zero vector if and only if U and V are scalar multiples of each other. And lastly, U cross V's magnitude is the area of a parallelogram having U and V as adjacent sides. And this can also be used if you get a question that says to find the area of a triangle, and that would just be half of the magnitude of U cross V. So next we have the triple scalar product, which is when you take the dot product of after you cross two vectors, and so you will result in a scalar answer, and you can take the cross product just like you do a normal cross product, but instead of having ijk in the top row, you put the u vector, and so when you multiply everything out, you will end up with a scalar solution. And this also is the volume of a parallelepiped, so you would take this triple scalar product if they asked you to find the volume of a parallelepiped. So here's an example problem for cross product. If we have vector u, 2, negative 2, and 4, and vector v, 1, 3, negative 1, find a vector that is both orthogonal to u and v. so in order to do that, we would take the cross product because, as we saw in a theorem earlier, finding a vector that is orthogonal to two vectors, you take the cross product. And so in order to do that, you can set up this determinant matrix, and you have I, j, k. And so to solve for I, you do the columns that don't involve the I. So you would do -2 times 2, or sorry, -2 times -1 minus 4 times 3. That's where you get the 2 minus 12. And then for the j, you do the 2 times -1 minus 4 times 1. And so that would be negative because we are flipping those sides. And then for k, you have 2 times 3 minus -2 times 1. So our final resultant vector will be -10i plus 6j plus 8k. So moving on to 11.5. 11.5 is about lines and planes, and so the theorem 11.11 shows that a line parallel to the vector b and passing through point P is represented by these parametric equations. So you can use these to solve for any parametric line in space. And then next we have the equation of a plane. So the standard equation of a plane will be in this standard form: ax a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And the a, b, c coefficients are actually the normal vector coordinates, so components, and that's what you use to denote the plane. And next we have some more equations about distance between a point and a plane. So the distance between the point and a plane will be projection of n of pq, and that is equal to pq dot n over magnitude of n. And same for theorem 11.14, distance between a point q and a line in space is magnitude of pq cross u over the magnitude of u. So next we have a small sample problem about finding the equation of a plane passing through these points. So do any of you guys have an idea of how you would approach this problem if you're given 3 points and you want to find the equation of the plane? You guys can write it in the chat if you want, or unmute yourself. Yes.
I think you find vectors A, B, and A, C, and then take the cross product. That gives you your normal vector. Then you.
Yep.
And then you. Oh yeah, and then you take a point A.
Yes. Perfect. So you would find the two vectors. You can do any two. You could do AB, AC, or you could do AB, BC. Doesn't really matter. So you find those two vectors by solving for those vectors using the points. And then once you take the cross product, you're solving for the normal vector. And so the normal vector will give you those coordinates. And then you can plug in any of the points that you have from before into the equation of the standard plane that we had earlier and solve for the equation of the plane. And you can even simplify it further to the more simplified version of the standard equation. So next, we just have arc length and surface area in 7.4. So definition of arc length, all you need to know are these equations, and both of these equations are the same. They're just in terms of different variables. So it's just the integral from over the interval of the square root of 1 plus f prime of x squared. And the surface area equation is pretty similar. We just add a couple more things. So the surface area equation is 2 pi integral of over the interval of the function itself times the square root of 1 plus f prime of x squared. And here is a small sample problem. So find the arc length of the graph of f of x over the interval 0 to 1. And so all we need to do is plug it into the formula. And our formula from before was the integral of square root of 1 plus f prime of x squared. And so here is the work for that. This is a pretty simple problem. And so we would just take the derivative first. So take the derivative of e to the x plus e to the negative x over 2. And when we plug that into the equation, the square root and the squared cancel out, and you can easily take the integral. So next we have parametric equations, and this is just the definition of a plane curve. And so we are basically using t as a parameter so that we can actually see over the time that it takes where exactly the curve is moving over a certain time, which is why we introduce a third variable. And so here's a small sample problem. And so this is where it becomes really important to remember trig identity. So can anyone tell me what trig identity we might use to eliminate the parameter here? Any ideas? You guys can type it in the chat if you want.
Okay, I'm drawing a blank, but maybe try using the r cosine theta is equals to x, and then just throw that in there.
It's actually a lot simpler than that. All we would need to do is use our trig identity, our Pythagorean trig identity. So we could use our cosine squared theta plus sine squared theta equals 1. And so we can isolate cosine theta and sine theta by taking over the coefficients to the other side. And if we square both sides of each equation, we can plug it into our trig identity, and we would get x over 3 squared plus y over 4 squared equals 1. And so that way we can eliminate the parameter theta. So next we have more parametric equations, and this is just involving calculus as well. And so this is just talking about how to take the derivative in terms of t. So you can find dy dx using dy dt over dx dt, as long as dx dt is not equal to 0. And then we have the arc length in parametric form. So this is also very similar to our original arc length equation. So arc length is equal to the integral over the interval of square root of dx dt squared plus dy dt squared. Next, moving on to polar. So polar functions are basically radial representation. So if you guys remember what the graphs look like, they're concentric circles. And so we can convert between polar to rectangular pretty easily with these equations. And so when we want to convert from polar to rectangular, we can use x equals r cosine theta and y equals r sine theta. And to convert from rectangular to polar, we can do tan theta equals y over x, and r squared equals x squared plus y squared. And so here is slope in polar form. This is a theorem telling you that if you find dy dx in terms of theta, you can do dy d theta over dx d theta. You're always going to get f of theta cosine theta plus f prime of theta sine theta over negative f of theta sine theta plus f prime of theta cosine theta. So you can memorize this theorem if you want to, or you can work out the whole thing. So it's up to you. And these are examples of different types of graphs, polar graphs. So limesons are going to be with equations that look like r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. And so if your a over b is less than 1, you're going to have a loop. If your a over b equals 1, you're just going to have a heart-shaped one, and then so on and so forth based on your a over b ratio. And then for rose curves, you have n petals when n is odd, or 2 n petals when n is even. So the equation usually looks like r equals a times cosine n theta, or a times sine n theta. And then for circles and lemniscates, circle equations are either r equals a cosine theta or r equals a sine theta. And then lemniscates are going to be r squared equals a squared sine 2 theta or a squared cosine 2 theta. So they're just examples of graphs that you might see. So for a sample problem, we're just convert the following rectangular equation to polar. So we have x squared plus y squared equals x. So anyone have an idea of which equation we would use to convert? Yes, go ahead. X squared plus y squared equals r squared.
No, I think you would throw in r cosine theta into the x and r sine theta into the y squared, and then throw r cosine theta into the x on the very end, and then put r on one side, I guess. Try. I don't know, somewhere along the lines. Just replace everything with r cosine and r sine or something.
Yeah, so those are all good ideas. So we're going to use a combination of all of those. So we have x squared plus y squared equals r squared. And we also have x equals r cosine theta. So we can actually use both of those and plug in r squared for the left-hand side and r cosine theta for the right-hand side. And then we can solve for r, and we'll get r equals cosine theta. So 10.5 involves area and arc length of polar. So area in polar coordinates, the formula you want to use is 1/2 integral over the interval of r squared d theta. And then for arc length of a polar curve, the arc length equation is going to be the integral over the interval of square root of r squared plus dr d theta squared. So that was the quick review of all of the topics. So now we will take a short 3-minute break and then go into 3 different breakout rooms, and each of the leaders will be working out practice problems from our exam review packet. So you guys can follow along with the leader. The leader will work out the problems on the board. And then you guys can definitely ask any questions you have, and also if you guys have any specific topics you want to cover, we can cover those problems first and then go on to less concerning topics afterwards. So You guys can let your leader know in your breakout room when the breakout rooms begin, but for now we'll take a 3-minute break and then start the breakout rooms. I think.
Yes, I see like a Microsoft OneNote.
Yes, perfect. Okay. So the exam review packet will be uploaded and you guys will be able to see it as well. But for now, we have the packet here and we have questions that from each topic. So are there any specific topics that you all want to see or go through first so we have enough time to cover them, or would you guys just like to work on it from the beginning?
I personally would prefer like either parametrics or polars, but anything is fine.
Parametrics and polars. Okay. Anyone else have any preference before we get started?
I would also like parametrics or polars.
Okay, cool. So we'll get started. We will get started with parametrics and polar. Let's see. Okay. So parametrics, let's start with this one. Okay, so this question says, find parametric equations. Are you guys all still able to see my screen? I'm not sure. Okay, I think so.
Yes.
Okay, perfect. So this question says, find the parametric equations of the line that passes through point P and is parallel to the line that is given here. So what do you guys think would be our first step? Anybody have any ideas? So
We could make it a vector.
So we actually don't need to do that, but let's see. So I can't. Sorry, I'm having some technology issues. 1 second. Okay. So point P is 1, 2, 3, and we have x minus 7 over 5 equals y minus 3 over negative 3 equals c over 2. Can everyone see my writing on the screen now? Yes, okay. So we have so we have A, B, and C. Our A is 5, and our B is negative 3, and our C is 2. And we also have X naught as 7, Y naught as 3, and Z naught as 0. So do you guys remember the equation where you have x minus x naught over a equals y minus y naught over b equals z minus z naught over c? And all of that you can convert into parametrics. Anyone recall that? Yes, okay, cool. So then we know that we can split this up into 3 different parametric equations. So we have x equals 1 plus 5t. because our coefficients are the ones in the denominator. And so somebody give me the equation for the y. Based on what we just did with this x. 1 plus 3t. Okay. So we had 1 plus 5t first. I'm pretty sure. We have 2 plus 2 minus 3t. And then for z, we should have 3 plus 2t. Does that make sense to everyone? Okay. So we'll move on to the next question. Let's see. So we have given points P and Q. Find the parametric equations of line segment PQ. So for this question, what would we do first? Anyone have an idea? So we can go ahead and make a line using PQ. That would be our first step. So to do that, we can form line PQ. So let me go back to our page here. And so we have P, our point P is 1, 2, negative 1. And our point Q is 2, 0, 1. So to form line PQ, we can simply subtract. And so we would get 1, negative 2, and 2. And then you can use any of the points to come up with the parametric equation for this. So to solve for the parametric equations, we can use point P, and so we'll use 1 to negative 1. So we can find the x, y, and z representations of each one. So we have x equals 1 plus t, and then we'll have y equals 2 minus 2t, and we have z equals negative 1 plus t. And this one says to find the parametric equations of line segment PQ. So our t's domain is going to be limited because it's saying to find it with the line segment. So our t will be within 0 and 1. But if we look at the next question, go back to our review packet here. We're on section 10 point. Yeah. So it says to find the parametric equations of the line segment PQ. And the next section is the same question actually, but it says to find the parametric equations of the line passing through P and Q. And so for that, we would switch it, our T's range, and it would actually be from -infinity to infinity, because we're looking at the entire line as a whole now. Any questions about this before we move on to the calculus parametrics? Okay, so let's move on to the next question. And next we have find the parametric, find dy dx at t equals 1, given these parametric curves. So this is section 10.3, and so now we're implementing calculus into
We can't hear you anymore.
how do we find dy dx? Is everyone able to see my screen?
You cut out for like a good 3 minutes.
Oh, really? Oh my gosh. Okay, where did you guys last hear?
So you had just shown us like the question itself, and we didn't get anywhere after that.
The parametric with the calculus question?
Yes, I think it was this one.
Okay, perfect. So this is the question, and it says, let's go back to the question so you guys can see it again. Yeah, so this is the question. Given the parametric curve x equals t cubed minus 2t squared plus 4t, and y equals 5t cubed minus 2, find dy dx at t equals 1. So how would we go about finding dy dx? Any ideas?
Take the derivative of x and y, and then put dx dt over dy dt.
Yes, perfect. So we're going to go solve for dy dt individually as well as dx dt. So to solve for dy dt, we can take the derivative of y with respect to t. So dy dt equals 3 times 5t squared. So we basically get 15t squared. And if we plug in 1, we will get 15, because we want to find dy dx at t equals 1. And next, if we solve for dx dt, we can do the exact same process. And so we'll take the derivative of x with respect to t, and so we have 3t squared minus 4t plus 4. And if we plug in 1, we have 3 times 1 minus 4 plus 4, and we end up with 3. Okay, good. So to solve for dy dx at t equals 1, we can just do dy dt over dx dt. And that is simply 15 over 3, which is 5. So it's going to be the answer to our part 1. Any questions about that? Okay. So next part tells us that we need to find, I'm pretty sure it says dy squared over d. Yeah, d squared y over dx squared. So that is asking us to find the second derivative. So back to our sheet here. So in order to find the second derivative, as the equation is going to be d squared y over dx squared equals the derivative with respect to t of dy dx over dx dt. So we had from our initial equation earlier, we had for dy dx in terms of t, we had 15 t squared for dy dt over dx dt, which was 3t squared minus 4t plus 4. So we need to take the derivative again of this with respect to t. And so in order to do that, we can just use quotient rule. So let's do that. First, quotient rule is low d high minus high d low. So low is going to be, let me write this out. So the low is 3t squared minus 4t plus 4, and the derivative of the top of the numerator is going to be 2 times 15t minus the top, which is 15t squared, times the derivative of the bottom, which is going to be 6t minus 4, all over the denominator squared, which is going to be just 3t squared minus 4t plus 4 squared. So now this is just the numerator portion, so we actually have to put it over dx dt again. So it was actually a common mistake, and it's pretty easy to forget to do that. So make sure you guys don't forget to do that, and remember to put dx dt on the denominator. So basically, to plug it in back here, we have this whole thing again, and we're just going to put this whole thing basically over 3t squared minus 4t plus 4 again. And so that basically increases the power of your denominator by 1. So now this is pretty easy. You don't necessarily have to simplify too much because we are plugging in 1. So we can go ahead and plug in 1, and you guys can actually work that part out on your own because it's just plugging in. Yes, so we do have to use the quotient rule over dx dt because for this problem, we use the quotient rule. It might not be like that for every problem because it might simplify out beforehand. So, but for this one, the easiest way to go about taking the derivative is to use the quotient rule. So all we have to do after this point is plug in 1 for t, and your answer will come out to be 20/9. So you guys can try this out, just so we have enough time to cover other topics as well, but we would just plug in 1 and then simplify, and you should get 20/9. Any questions about this? All right, so let's move on to another problem then. Okay. So the next problem in this section says, find the horizontal and vertical tangents of x equals 3 cosine squared theta and y equals 2 sine 2 theta. Okay, so let's go back to our page here. So it says to find the horizontal and vertical tangents of x equals cosine 3 cosine squared theta and y equals 2 sine 2 theta. So what do you guys think? How would we find the horizontal and vertical tangents of each one? Yep. So for horizontal tangent, we want dy d theta to equal 0. And dx d theta also should not be 0. Anyone know what it means if both dy d theta and dx d theta are 0 at the same time? Yes, it is not smooth there. So that's how we would find for horizontal, and for vertical, it's the same thing but flipped. And so we want dx d theta to equal 0 and dy d theta to not equal 0. So to do that, first we want to see where dy d theta is equal to 0. So dy d theta equals to 0. And so first we need to find dy d theta, and to do that, we can take the derivative of y with respect to theta. And so we would get 4 times cosine 2 theta. And so where are the points that equals 0? Can anyone tell me? So we can just set this equal to 0. We have cosine 2 theta equals 0. And theta will basically be equal to 0 at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And for dx theta, we do something pretty similar. Oh, you guys can't see my screen. Sorry about that. So there, hopefully everyone can see that now. So for dx theta equal to 0, we can take the derivative with respect to theta again, but this time for x. So the derivative will be equal to negative 6 times cosine theta sine theta. And so we basically use the chain rule to find the derivative. And so now we can solve for the points where it equals 0. So cosine theta sine theta is also equal to sine 2 theta based on our identities. So we have actually negative 6 sine 2 theta. And so then we can just find the points where sine 2 theta is equal to 0, and those points will end up being where theta equals 0, pi over 2, pi, and 3 pi over 2. So now we see all points where each of them are 0, and there are no theta values where both are equal to 0 at the same time. So that means we don't have any points on the graph that are not smooth. And so now we can just plug in points to find, plug in theta values to find coordinate points. So we have theta equals pi over 4. So for that, if we plug in pi over 4 into x and y, theta equals pi over 4, and we plug that into x and y, we will end up getting 3 over 2 and 2 as our first point for our horizontal tangents. And same in every single theta value, we will get theta equals, if we plug in 3 pi over 4, we should get 3. Is everyone still able to hear me and see my screen? It says my connection is poor, so hopefully everyone is still able to see me, or sorry, see my screen. So if we plug in 3 pi over 4, we will get 3 over 2, negative 2. And so similarly, we can do that for all of the other theta values to find the horizontal tangents. So then once we figured that out, we know the horizontal tangents will end up being at points 3 over 2, 2, and 3 over 2, negative 2. Because when we plug in again, we will basically get these exact same points for 5 pi over 4 and 7 pi over 4. So now we only have to show those two, and we get horizontal tangents at those 2 points. So similarly, we can find the vertical tangents, and we have plug in our first theta value of 0 into both x and y. And when we plug it in, we should get 3, 0. And if we do the second one, pi over 2, we will get 0, 0. And similarly to our horizontal tangents, if we plug it in again, we will get the exact same 2 points. So our vertical tangents will be at 3, 0, and 0, 0. So this was a pretty straightforward, simple problem. Any questions about that? Okay, so let's move on to the next problem. And now we will be getting into arc length of a parametric curve. So the next question asks to find the length of the curve, and we have two parametric equations, x equals arc sine t, y equals ln square root of 1 minus t squared over this interval. So we are going to mainly be setting it up and then set up the work, and then the algebra you guys can confirm on your own time as well, but we will mainly set up together and then work through the concept. So anybody remember the equation for arc length of parametric curves? Down. So we have x equals arc sine t, y equals ln of square root of 1 minus t squared, and our interval is 0 to 1/2. So our equation for arc length is integral from a to b of square root of dx dt squared plus dy dt squared. dt. So make sure you guys remember this formula. All the surface area and arc length formulas are pretty similar, so make sure you don't get them confused. So now, in order to be able to plug in our things, all of our components into this equation, you have to take the derivatives first. So if we do dx dt, we have derivative of arc sine t, and so we will get 1 over square root of 1 minus t squared. So make sure you guys remember all your derivatives of all the trig functions and arc sine, arctan, all of those, because you guys will still be using those. And then for y, dy dt, we're going to take the derivative of ln of square root of 1 minus t squared. So we'll have 1 over square root of 1 minus t squared, and then we'll multiply it by the derivative of the inside, which is going to be 1/2. So we'll have 1 over 2 square root of 1 minus t squared times, again, the derivative of the inside of the square root, and we'll have negative 2t. So that's our derivative of dy dt. So now we want to plug that into our equation of surface area. So we have s equals integral from 0 to 1/2 of the square root of 1 over square root of 1 minus t squared squared, and then plus So we can actually simplify this a little bit over here. And so if we simplify our dy dt and multiply it all out, our square roots will actually cancel out, and we will end up with a negative t over 1 minus t squared. So we can plug that in instead of having our entire dy dt. So plug in negative t over 1 minus t squared, all squared dt. And so now we can simplify a little bit by multiplying out the square roots. So let's do that. Integral of 0 to half of square root of 1 over 1 minus t squared plus t squared over 1 minus t squared squared still. And so anybody have an idea of what our next step would be? Are you guys all still able to see my screen? Okay. So our next step will actually be, we'll just try to make a common denominator. So we can do that by, since we kind of already have a common denominator, we just multiply the first term by also 1 minus t squared over 1 minus t squared. So if we can get it to a common denominator, we'll have s equals integral of 0 to 1/2 times square root of 1 minus t squared over 1 minus t squared plus t squared over 1 minus t squared. And so our numerator actually cancels out the 2t squared. And so we'll have integral from 0 to 1/2 of square root of 1 over 1 minus t squared dt. And so this actually works out because now our square root and squared can cancel out, because this is kind of the same thing. We can actually rewrite this instead of having the square at the bottom, we can rewrite it as the whole thing squared, since 1 squared is still 1. And now we can cancel out our square root. Any questions so far? Okay. So next, once we cancel those out, we're left with just integral of 0 to 1/2 of 1 over 1 minus t squared dt. And so to integrate that, what do you guys think we would need to use? What is the easiest method we can use to take this integral that you guys remember from maybe Calc 1? Any ideas? You guys can type it in the chat or say it out loud. Okay, so that's okay, but we will probably, the easiest way to do this is to use partial fractions, because we can factor out the denominator into 1 plus t and 1 minus t. So how many of you guys actually remember partial fractions? Make sure you guys remember all the integration methods that we learned from 2417 as well, because you're definitely going to be reusing that in problems like these. So we will use partial fractions and split this up. So basically we can rewrite this integral 0 to 1/2 of, we can use any variables we want, a over 1 plus t plus b over 1 minus t dt. And so we can use partial fractions and solve for a and b. And so I'm not going to solve the whole thing out, just so we can get to a little bit more of the packet. But for a and b, we will actually get 1/2 for each one. So once we find a and b, we can plug it back into our original integral and take the integral. So make sure you guys go over partial fractions, since it is something we learned last semester. Make sure you go over it on your own time and just brush up on that, because you could be asked an integration question about that. Not directly, but through like another topic, kind of like this question. So we'll take the integral from 0 to half of 1/2 over 1 plus t plus 1/2 over 1 minus t dt. And that's a pretty simple integral. If you remember, it's just going to be a natural log integral. So we have 1/2 of ln. We can actually take out the 1/2 since we have 1/2 in both. So we can have 1/2 ln of 1 plus t plus ln of 1 minus t. And that's from 0 to 1/2. And so from there, you can just plug in 1/2 and 0 into both the terms, and then you should get ln of 3 over 4 to the, or you should get half ln 3 over 4. And so, as you know, according to log rules, you can write this in many ways. So any answer would be fine. You could do ln 3 over 4 to the half, or ln of square root of 3 over 4. So anything is fine. So that's the final answer. Any questions about this one before we move on? All right. So next on our topics, we can move on to polar now. So these are pretty simple. Let's do these conversions from rectangular to polar form. First, we have convert to -2, -4 from rectangular to polar. And so we can use our two equations that we have. We could do x squared plus y squared equals r squared. And we can do theta, or tan theta, equals 1 over x. So we're trying to get from x comma y to r comma theta. So to solve for r, we have r equals square root of x squared plus y squared. So that is the same, we can plug that in. We'll have -2 squared plus -4 squared. And so that comes out to be 4 plus 16, so that's square root of 20. And you can simplify that further if you want, but it's not necessary. And to find theta, we have tan theta equals y over x, so negative 4 over negative 2. And then we can simplify that and we basically get theta equals arctan of 2. And so you can leave it in this form because we don't know the exact arctan of 2, so you can leave it like that. But do you guys think that this is our final theta value, or is something missing?
Maybe bounds.
Yeah, kind of. So if you look at our original point, it's negative 2, negative 4, right? So what quadrant is that in? So negative 2, negative 4 is actually in quadrant 3. So the theta value we found, though, is not yet in quadrant 3. So we actually need to shift it to quadrant 3. And so you can just do that by adding pi to it because, as you know, our tan values or the theta values for tangent will be the same across from each other if you look at the unit circle. So if we add pi to this theta value, we will be moved from the first quadrant to the third quadrant. So our final answer is actually going to be, in terms of our comp theta, we will get 2, or we had square root of 20, comma, pi plus arctan 2. Okay. So our next question is to convert 0, negative 4. And so that's also really simple. So we'll do that really quickly. 0, negative 4 to polar. So same way, we're going to do the exact same thing. We have r equals square root of x squared plus y squared. So we can do square root of 0 squared plus 4 squared, or negative 4 squared. And so we will get 4. And theta is also, again, arctan x, or sorry, y over x. And so we can do arctan of negative 4 over 0. And so we have to find where tangent becomes undefined, basically. So if you remember the unit circle, tangent is undefined at pi over 2, 3 pi over 2. So this one is going to be 3 pi over 2 because it's 0, negative 4. So keep in mind what your original coordinate is and then choose your theta value accordingly so you are in the correct quadrant. So for this one, theta is going to be 3 pi over 2. And so our final value, our final answer is going to be 4, 3 pi over 2. So our next question is similar, but we're going to be converting from polar to rectangular. So let's see what it says. Here it is. So here are the equations.
Oh, excuse me, I had a question about the last one that we just did.
Yes.
So how
Go
come
ahead.
it's 3 pi over 2 and not just pi over 2?
That's a good question. So as I was saying, tangent is undefined at pi over 2 as well. But if you had put pi over 2, if you look at the unit circle, pi over 2 is actually kind of like in between the first and second quadrant, right? So that's telling you that you're on the top half of the axes. But our original coordinates were actually 0 and -4. So -4 is a negative numbers on the negative y-axis. So you wouldn't use pi over 2 for this situation because that theta value isn't in the correct quadrant. So you would have to use the next theta value where tangent is undefined, and the next one would be 3 pi over 2, according to the unit circle. Does that kind of make sense?
Yes, that makes sense. Thank you.
No problem. Okay, so now we can move on to the next one. Let's go back over here. Okay, so we're going to convert r equals 2 cosecant theta plus 2 secant theta. And we can use our conversion equations from earlier. So we can put this into first a form that we can work with, because we have x equals r cosine theta and y equals r sine theta, right? So we need to get it into those forms. So we have, this is the same as if you do 2 over sine theta. And this is the same as if you do 2 over cosine theta. So now we have to get it into a form where we can plug in things. So if we get it to a common denominator, we can try to work from there. So if we multiply the first one by cosine theta over cosine theta, and the second one by sine theta over sine theta, we can get it to a common denominator. And so our resulting fraction will be 2 cosine theta plus 2 sine theta over sine theta cosine theta. And going from here, we can try to simplify as much as possible so we can plug in. So we can multiply the denominator over to the other side. By doing that, we will be able to plug in. We have r sine theta cosine theta equals 2 cosine theta plus 2 sine theta. And so now we have to split up the left side somehow. And so we can actually do if we multiply both sides by r, then we can actually use that r and then have, we can start noticing those x equals r cosine theta and y equals r sine theta equations. So the idea behind this, or like the questions that they might ask, they look kind of like this. You just need to do your best to recognize like what you can do to manipulate the equations. So going from here, we have, if we multiply both sides by r, we have r sine theta cosine theta times r equals 2 cosine theta plus 2 sine theta times r. And so now we have r's for each of the trig expressions. So we have r sine theta times r cosine theta, and that equals 2r cosine theta plus 2r sine theta. So now you can actually plug in our equations that we talked about originally. So r sine theta is the same thing as y, and r cosine theta is the same thing as x. And we can do the same for the other side. So we have 2r cosine theta, so that's 2x. And we have 2r sine theta, and that's the same as 2y. So our final equation is this, or you can simplify it further if you want. You can bring over the y to the other side. So let's do that. We have yx minus 2y equals 2x. And if we take out the y, we have x minus 2 equals 2x. And now you can bring the x minus 2 to the other side, and you'll end up with y equals 2x over x minus 2. So if you want to simplify it all the way, this would be your final answer. Any questions about that? Okay, so let's do the next one. The next one's a little bit different. So the next one says r equals 4 cosine theta plus 6 sine theta. And so for this one, we need to identify what kind of curve it is. So we can immediately plug in the equations that we know. And so we have r, so we can multiply both sides by r first, because as we know, to be able to work with the cosines and sines, it has to be r cosine theta or r sine theta. So if we multiply both sides by r, we'll have r squared equals 4r cosine theta plus 6r sine theta. And so now we can start plugging in the equations that we know. So for r squared, our equation that we used earlier is x squared plus y squared. And for 4r cosine theta, we have r cosine theta, which is equal to x, so we can do 4x. And then for r sine theta, we have y, so we can do 6y. So now we have x squared and y squared, as well as x's and y's. So we're going to try to come up with an equation that is actually telling us what kind of curve it is. So to do that, how do you think we can combine the x's and the y's? Do you guys have any ideas? Okay, so for this one, we actually want to complete the square. So if you guys remember from algebra or something, we complete the square in order to figure out what kind of curve it is. And so we can bring all of them to one side first. So we have x squared minus 4x, and then we have plus y squared minus 6y equals 0 right now. And so we can complete the square. And if you guys remember how to complete the square, we will add in extra constants, and we can subtract it from the same side and bring it over to the other side in order to maintain the same equation. So for completing the square for the first one, x squared minus 4x. In order to complete the square, you have to add 4, which then transfers into x minus 2 squared. So I would also recommend brushing up on how to complete the square so that you guys do know how to do that for the exam. And similarly for this one, you have x squared, or sorry, not x squared, you have y squared minus 6y. And to complete the square for this one, you divide the coefficient by 2 and squared, so you have plus 9. And that goes down to x, y minus 3, also squared. And so since we added 4 as well as 9 to this side, we have to do the same to the other side. So our final equation will end up being x minus 2 squared plus y minus 3 squared equals 13. So from this equation, what kind of curve do you guys think it is?
It's a circle.
Yes, exactly. So this is a circle with a radius of square root of 13, and its center is at 2, 3. So that is this question. Any questions about this one? All right, so let's move on to the next one. Okay. So it says, consider the cardioid C given by r of theta equals 2 plus 2 cosine theta over 0 to 2 pi. And we want to find the points on C where the tangent is horizontal and vertical, and also find the equation of tangent at pi over 4. So we can do all of this. Let's move over to our page. All right. So we have C equals, or I guess C is just the cardioid name, but the function is actually r of theta equals 2 plus 2 cosine theta. And that is over the interval of 0 to 2 pi. So we want to find the points where the tangent is horizontal first. So in order to do that, we have to split it up first into in terms of x and y, right? Because we need to find dx d theta as well as dy d theta. So if you guys remember from our equations earlier, we have x, in this case, x of theta is going to be r cosine theta, and y of theta is r sine theta. And so this is how we can split up our r of theta into these. So for x of theta, we will get 2 plus 2 cosine theta times cosine theta, because we're just plugging in our r into these r's right here. And for y, it's the same thing, 2 plus 2 cosine theta times sine theta. And so we can simplify these out, and we'll get 2 cosine theta plus 2 cosine squared theta. And this one goes to 2 sine theta plus 2 cosine theta sine theta. And so we can make this a little bit easier for us already by switching this into an identity that we know. And so we can switch this identity to sine 2 theta. So now to find dx d theta, we're just going to take the derivative of x with respect to theta. And so that will just be negative 2 sine theta. And then we'll have plus 4 cosine theta times sine theta. And that is going to end up being a negative sign as well because of the sine theta derivative, or the cosine derivative is going to be negative sine. So we have negative 2 sine theta minus 4 cosine theta sine theta. And so again, we can switch this identity to make it a little bit easier for us later on. And we have negative 2 sine theta minus 2 sine 2 theta. Now we can find the derivative of dy d theta. And for that, we just have 2 cosine theta plus 2 cosine 2 theta. So now to solve for dy dx, we'll do it just like how we did earlier for the parametrics. Dy dx is the same as dy theta over dx d theta. So if we do that, we have 2 cosine theta plus 2 cosine 2 theta over negative 2 sine theta minus 2 sine 2 theta. And so we can simplify this a little bit by taking out the 2's in the front, as well as we can take out the negative sign as well. And so that'll just come out to negative cosine theta plus cosine 2 theta over sine theta plus sine 2 theta. And so if you guys remember the theorem that I showed you earlier while we were going through the slides, you could memorize it like that with the formulas they gave you and just plug it in, or you can solve it out like we just did and you will get the same answer. So now to find the horizontal tangent, just like we did earlier, dy d theta should be equal to 0, and dx d theta should be 0 at the same point. So let's solve for those. So the points where dy d theta are equal to 0, we can set the numerator equal to 0 and make sure the denominator is not 0. So let's see. We'll set each one individually to 0 to see. So 0 equals cosine theta plus cosine 2 theta. And now we can, the only way we can really solve for this is if we change the identities a little bit. So if you guys remember, cosine 2 theta has another identity that we can use, and so that identity is actually 2 cosine squared theta minus 1. And so this gives us kind of a quadratic equation that we can factor out now into two different factors, and we'll have 0 equals cosine theta plus 1 times 2 cosine theta minus 1. And so now we can set each individual factor to 0, since if that one of them is 0, it's going to make the whole thing 0. So if we have cosine theta plus 1 equals 0, then we know cosine theta equals -1. So wherever cosine theta equals -1 is where we want to find, and that is theta equals pi for this within our interval, because our interval is only 0 to 2 pi. And do the same for this side, so we can just do 2 cosine theta equals 1. So cosine theta equals half. And so those values, wherever cosine theta equals half, is going to be pi over 3 and 5 pi over 3. So now, in order to do the other one, we're going to set the denominator also equal to 0 so we can check. So let's set the denominator equal to 0. So we have 0 equals sine theta plus sine 2 theta. And so we can plug in actually each one. We don't need to set this equal to 0 yet, since this is still part A. We can plug in each of these theta values that we found here. And that might be a little bit quicker, and we can solve for each one and see if any of them actually come out to 0. So if we plug in pi into here, we're going to get we're going to get sine pi plus sine 2 pi, and that is going to get you 0. The sine pi plus sine 2 pi is 0 plus 0, we're going to get 0. So we know that we can't use this value because at this point dx d theta is equal to 0, so that's not going to be one of our horizontal tangents. And then to confirm, we can just plug in pi over 3 and 5 pi over 3 also for each one. And for those, you will end up getting -2 square root of 3 for pi over 3, and you'll get 2 square root of 3 for 5 pi over 3. So I'm not going to work out all of those calculations since you guys can plug those in on your own and check, but that confirms that those two are going to be our horizontal tangents. So we do have horizontal tangents at pi over 3 and 5 pi over 3. And so now to go back and actually find where they exist, you have to find in coordinates of our theta, right? So we already have our theta values of pi over 3 and 5 pi over 3. And now you can just go in and plug these in into r theta and solve for the corresponding r values. And once you do that, you will get 3 comma pi over 3 and 3 comma 5 pi over 3. So those are going to be your horizontal tangents. Can everyone see my screen? I don't think so.
Yes, we can still see it.
Okay, perfect. Okay, so as I was saying, our final horizontal tangent values are going to be 3, comma pi over 3 and 3, comma 5 pi over 3. So let's see. I'm going to stop sharing for a second and then reshare because it's saying that it's not working. Let's see. Okay, hopefully this works. All right, so next is going to be the vertical tangents as well as finding tangent lines. So I'm not going to go over vertical tangent because it's the same process we just went through. So you guys can try that on your own. And lastly, to find the horizontal tangent, we are running out of time a little bit, so I'll just briefly talk you guys through how you would do that. But you will basically just plug in theta equals pi over 4 into dy dx. So I'm sure you guys could probably figure that out. To find a horizontal or to find a tangent line at a specific point, you plug in your theta value. And so you can do that and solve and check your answers with the key, but all the materials will be posted online as well as the YouTube link for the recorded session. So you guys can watch the recording again as well as work through the rest of the problems we weren't able to get to today, practicing for your test. So do you guys have any last questions before we end the review?
Yeah, you said the review will be up on the website or be emailed?
Yes, so it will be, the YouTube video will be on the peer tutoring YouTube channel. The link is, I can send the link, but it will be up on there, and the materials will be linked to in the description box. So the packet as well as the PowerPoint can also be linked there. So you guys will have those materials to practice.
Okay, thank you. And you said the group channel?
I'm sorry, what did you mean?
You said it was on the
Oh,
SEC
YouTube.
channel?
It'll be on the YouTube.
Oh, YouTube channel, sorry.
Yeah, sorry about that. Yeah, it'll be up on the YouTube channel.
Okay, then thank you so much.
No problem. I'm gonna stop recording now.